Welcome to another video from explainingcomputers.com. Earlier this year I took a temperature, pressure and humidity sensor and used it to build a Raspberry Pi weather station that recorded data in a spreadsheet. To my surprise, this turns out to be a very popular project, and so this time I'm going to take it further by building a homemade anemometer so that our Raspberry Pi weather station can also record the speed of the wind. Now, I want to stress from the start that this is not a video about building a perfect anemometer. Rather, what I'm doing here is a low-cost Raspberry Pi project which we're going to use to learn about all kinds of things, including measuring rotation using an optical sensor and writing associated Python code. So, in this project we're going to be using this Raspberry Pi 3 B+, but you can use any model of Raspberry Pi computer. Right now, the BME280 sensor we used in the first Raspberry Pi weather station video is connected to the Pi, but for now we'll disconnect this, but we'll be wiring things up in this project so we could add this sensor back in again if we want to. And the sensor we're going to be using in this video is this one, which is an infrared reflectance sensor which Adafruit sell for $1.95 and which I purchased from Pimeroni for £2.10. So let's open up this little bag. There we are, and in here we have two resistors whose purpose will become obvious, and we've also got the sensor itself. And if we take a closer look at this, what we have here is two components in one package. We have got an infrared LED and an infrared phototransistor. And the idea is that the LED will emit infrared radiation, infrared light, and if there's a reflective surface above the sensor, it will be reflected off the reflective surface back to the infrared phototransistor, which will trigger its gate and we'll be able to register that on the Pi. And back in my Raspberry Pi GPIO input video, I wired up one of these sensors and showed how it can be used to turn on an LED when it detected a black mark on a piece of white cardboard. But you may ask, how are we going to use a reflected sensor like this to measure the speed of the wind? Well, the answer is over on this cutting mat we've got various other things we'll be using in this project. For a start, there's a couple of ping pong balls. That's always rather exciting, isn't it? And we've also got an old biro. We've got to have an old biro. We've got some M3 nuts and bolts. We've got a stand in the knife to help us out, and we've got also here some liquid polystyrene adhesive. And we're going to be using that with this stuff. This is a 2mm high impact polystyrene sheet, HIP sheet, sometimes branded as Plasticard, and I'll give you more information in the video description on how you get hold of this product. Anyway, what we're going to do is to take the two ping pong balls and to cut them in half to make 4 cups, which will then mount on arms sticking out from the biro. We'll then mount this contraption in some sort of box, and in theory when the wind blows it will spin around. We'll also add a black disc with a white mark on it to our biro axle, which should allow us to monitor rotation using the reflectance sensor. And then finally, by taking the distance between the cups and multiplying by pi, we should be able to work out how far the wind has travelled in 1 anemometer revolution, which will allow us to write some code on the Pi to calculate the speed of the wind. So that's the theory. Let's now see if we can put it into practice. Right, as you can see, things have now progressed. Stanley the knife has been hard at work, helping me make these 4 little arms for the anemometer. And I've got a hole drilled in them as well, and I've got the ping pong balls, which you can see I've cut in 2, and these have got holes in the top 2, and the principle is we're going to use the nuts and bolts to attach these arms to the cups and to attach them to our axle, which is the biro. I've no idea if this is going to work, so all we can do is to put it together and see what happens. And so by the magic of filmmaking, here we are. I've now put the vanes together and it seems to have worked pretty well. I thought when I started this that the most difficult part of the whole project would be holding ping pong balls onto the end of little arms onto some sort of axle, and that seems to have worked. It's held together just with the liquid cement onto the biro as well, which I think is ABS plastic, so that's also been solvent welded quite successfully using the solvent I've been using to do that. And hopefully this will work. If I just stand it so you can see it like that, this obviously will be in a proper mount. It's standing on the ballpoint pen, obviously ballpoint, which I'm hoping is be a good axle. Well, I'll just hold it like that, which is not ideal, but if I blow, yes, we have something that rotates when it's windy or artificially windy inside. So we can now move on, I think, to building some sort of enclosure for this where we can put the sensor under here and we can record the rotation of our anemometer vane. Greetings! Here I am back again, and as you can see I've now fitted a disc to our axle, which was easier said than done, and on the disc there is this piece of white plastic which came from a piece of a buttery spread container, and this is stuck on so that in theory our sensor will be able to detect that as this thing spins around. And over here I built a little plastic card housing, and this will eventually be bolted to the top of a long wooden post so we can get the anemometer nice and high up. You want to measure wind speed some distance from the ground. And inside this box, as you can hopefully see, we've got our sensor, which is currently just temporarily mounted with a piece of blue tack putty so I can get the position absolutely right. And it's been soldered to this 6 meter length of a telephone flex, which is very handy 4-core cable to solder to the sensor with its 4 connections. So let's take our axle and put it inside. It just goes into a little notch down there and that down there. And then there's a top piece which drops in. If I can get it in, something like this. This does bolt on, but we'll just put it on like that for now. And this thing will therefore stand up and hopefully, yes, it will rotate without any problems at all. It's a bit jittery, as you can see. It's not the best spinning thing in the world, but we can partially compensate for this in software, as we will do a bit later in the video. Anyway, for now you're probably wondering what goes on at the end of this cable, and it's terminated in this, which is a small piece of strip board which contains the resistors which came with the sensor, plus an extra one I've thrown in for good measure, and it's got jumper leads here going out to the Raspberry Pi. And if you want to know exactly what's going on here, you can see the soldering there on the back. If we look at this circuit diagram, we can see the sensor's LED is connected to 5 volts and ground pins on the Pi via a 470 ohm current limiting resistor, and the phototransistor is then fed 3.3 volts from the Pi with its emitter connected to GPIO pin 12 via a 1K current limiting resistor, which will protect the pin in case of a coding error. And finally, there's also a 10K pull-down resistor also wired to the GPIO pin. This is all a very standard kind of setup, and if you want to know more about pull-down resistors and current limiting resistors and things like that, look in my Raspberry Pi using GPIO inputs video. Anyway, let's get this all connected up and running, and here we are. The anemometer is now connected up to a functional Raspberry Pi, and if we go across the Pi's desktop, I'm running here the Genie editor, in which initially I've written a very simple piece of a test code. And all this does is to import the GPIO libraries. It sets pin 12 as a GPIO input using board numbering there, and it runs an infinite loop here, because while true is always true, which says if GPIO input 12 is equal to 1, in other words it can see white, it's going to print white, else it's going to print black. And this runs inside a try-finally combination, so we always clean up the GPIO pins at the end, even though we're going to crash out of this code. So if we bring up a shot of the anemometer and we run this code, there it is, it says black, but if I rotate the thing eventually somewhere, there we are, there's white, black again, and if I spin it around like that, it goes back and forth between white and black. You can see the basic principle, this thing is working. So let's close that code down, and over here I've written some code which will actually calculate wind speed. And this starts off exactly the same way, importing the libraries, also importing the time library here and setting up the GPIO pin. And then there's various variables which are defined. The first one is the anemometer vane diameter. This is the distance between the cups in millimeters on the anemometer, which for me is 106 millimeters. Obviously here enter the value here for anything you built yourself. And then we work out the vane circumference using vane circumference equals obviously vane diameter over 1,000, move it into meters and multiplying by pi. 3.1415 is perfectly adequate in terms of accuracy for what we're doing here. We also set what's called an anemometer factor, which here I've set to 2.5. And this basically accounts for the fact that no anemometer is perfectly efficient. There will be a loss of energy as wind hits the vane and turns it round, and there'll be friction in terms of the operation of a system. We know ours is a bit jittery, so all anemometers have to have a number multiplied by their final result to account for the practicalities of the real world inefficiencies. This value seems to be anywhere between about 1.25 and 3, depending on different anemometers. I've guessed at 2.5 here. That might be a bit high, but I think it's not that unreasonable, as you'll see for various reasons a bit later on. We then measure wind speed. We start out by measuring wind speed. That seemed a good idea. And then we define some variables. Rotations is going to be a floating point variable there, and we set it initially to 0, and we set trigger to 0, which is going to be whether we triggered or not our sensor. We're then going to define a variable called end time, which will be the current time plus 10 seconds, which basically uses time plus time, which returns the current time in seconds. We add 10 to that. And we're also going to gather the initial state of a sensor. So sensor start is going to be the current state of a GPIO input, which could of course be seeing black or white. We don't know when this thing starts. We then got a loop, which is actually going to count rotations. So it's going to say, whilst the current time is less than end time, it'll keep going through. And then if GPIO input 12 is 1 and trigger is 0, it'll add 1 to rotations and set trigger to 1. So it won't do it again if the thing hasn't moved when we come back next time. And here it's also going to print recorded a trigger, just so we can see what is going on. And then if GPIO input 12 is 0, we're going to set trigger to 0, and this thing will keep going around, adding to rotations as we go through. And after various experimentation, I've found you need a tiny little delay in this loop to keep things stable, so we've got a time sleep 0.001 of a second, very small time sleep. Then, once the loop is finished, we can work out what's going on, but first of all, we want to account for the fact we'll have got a rotations of 1, even if the thing didn't move and it was seeing white at the start. So here we basically say if rotations is 1 and sensor start was 1, if it was seeing white at the start, we'll put rotations back to 0 to try and get things most accurate. We then work out the actual wind speed itself. Rotations per second is going to be floating point variable of rotations divided by 10. And wind speed in meters a second will be rotations per second times the vane circumference times the anemometer factor. Finally, we're going to print the results. We're going to print out rotations over 10, wind speed in meters a second, and wind speed in miles per hour, by which you simply multiply by 2.237 to get it right. And that's all nicely formatted with this code here. And then finally, as usual, as you should with GPIO stuff, you've cleaned up your GPIO pins. So let's bring up a shot of the anemometer. There it is, and we'll run the code like this, and it's measuring wind speed. And what I'm going to do is actually nothing to start out. So I'm not going to rotate the thing at all. I'm just going to blabber on for 10 seconds, and we will get a result at the end. There we are, 0 rotations a second. Obviously wind speed is 0. I just wanted to check it gave you 0 when nothing had happened. So we'll press a key on that, and we'll now run it again. And this time, I'm going to do some blowing on it. It'll record triggers, and at the end of that period of time, there we are, it did 23 rotations, 2.3 a second, wind speed is 1.19 meters a second, or 4.28 miles an hour, which is all very good. Things seem to be working. So let's go back to the code, and I think I'm going to get rid of the bit that prints recorded a trigger, because that's clearly just there for testing. So we'll get rid of that like that and resave our code file and save. And if we just go back to the anemometer, I'm going to bring in this. This is a rather wacky piece of equipment. This is a computing cleaning device which has a very high pressure air output. If I just turn it on, that's a very, if you can still hear me, that's a very high pressure air output. So let's go back to the code and run the code. And I'm going to use this thing to there we are. We've got, that was very exciting. We've got some results here, 116 rotations, and it wasn't even forced at it for the whole period of 10 seconds, of course. And we've got, well, a wind speed of 9.66 meters a second, 21.6 miles an hour. If you get this just right and run it for the whole period of time, you get about 30 on that test. And that's why I think my anemometer factor is about right. But anyway, it seems things are working. We've successfully put together a Raspberry Pi anemometer. Right, just before we do an outside test, I've added a BME 280 sensor back onto the Raspberry Pi, and I've also written some combined code, which puts together what I've just shown you for measuring wind speed with what I showed you for measuring temperature, pressure and humidity in my last Raspberry Pi weather station video. So what this piece of code will do is to record temperature, pressure, humidity and wind speed every 10 minutes into a spreadsheet. And I won't go through this in detail because it does combine two things I've already shown you. It basically imports all the libraries we need, sets up GPIO, deals with the variables for measuring wind speed, deals with initializing the BME 280 sensor, and then loads in a workbook where we're going to be saving our results, and then has a massive loop which both reads the temperature, pressure and humidity sensor and takes the wind speed measurements, and then down here prints out the results and adds things to the spreadsheet. So let's just test this out, show you it's working. So we'll just bring up a shot of the anemometer and run the code, and I'll give it some artificial wind. This will be running for 10 seconds doing its stuff. No output on the screen whilst it's doing that, but hopefully in a second something will happen. There we are, it's adding this data to the spreadsheet, temperature, pressure and humidity, and also a wind speed. And this will continue on every 10 minutes, so we'll actually go into that for now and stop it because we'd be here forever. But if I just bring up the spreadsheet, there we are, and you can see the first row of data has been recorded with a date and a time and the values we've just been talking about. So what I'm going to do is to get rid of this row of data because we don't want it there when we've just been doing a test. We'll delete that row, save the spreadsheet again, and everything's now ready to do an outside test. Right, here I am again. It's now the next day. There are some little white fluffy clouds chasing across the sky, and the anemometer has been mounted at the top of an 8-foot pole in my garden. And it's going around, at least at the moment, and it's connected to the Raspberry Pi, which is in my garage, so it's also outside. But I am inside here on my laptop, where I've connected to the Raspberry Pi via SSH. And I'm going to run the combined code now over SSH like this. It should be taking the first measurement and hopefully show us a measurement in a second. Oh, it's very exciting. Are we going to see some measurements coming across? Has 10 seconds passed? We don't know. It always seems a long time when you're counting out 10 seconds. There we are, look. 10.4 degrees out there, various pressure and humidity readings, and a wind speed of 1.17 meters a second. So what I'm going to do now is to leave the Pi putting data into the spreadsheet, and we'll come back in a few hours. Well, here we are back again after an afternoon of weather. It's been pretty varied. It was sunny initially, then it got rather dull. We've had a rain shower, but the anemometer is still spinning around. It survived the weather, which is rather good for something that measures the weather. And if we look here on the Pi's desktop, here is the spreadsheet of the data it has produced. It has worked. I'm always pleased to see when things work and produce data as they should. So as you can see, we've had a variety of, well, temperatures have been going down. I guess they do in the afternoon, particularly in February as it is now. Pressure's gone up a little bit. Humidity's gone up quite a lot. It rained in the middle of that. I think it rained around here, but not absolutely certain. And the wind speed has been variable. As you can see, it's not been massively windy, except on a few occasions the thing went round very, very fast. But of course, it wouldn't necessarily coincide with when a measurement was being taken. Anyway, I'm very pleased with this. I was pleased when I put the anemometer on the pole this afternoon and it started spinning. It's great when you can take some ping pong balls and an old biro and a sensor and things like that and actually generate some meaningful results. So there we are. We've managed to add a functional, if not perfect, anemometer to our Raspberry Pi weather station. And we're not finished yet, not by far. Not only do I have plans to continue to add sensors to the Raspberry Pi weather station, but I'm now musing on the idea of taking a Raspberry Pi and using it to control the cultivation of plants and to monitor the cultivation of plants in this somewhat dilapidated greenhouse. There must be lots of Raspberry Pi sensor and associated projects we can do here. But now that's it for another video. If you've enjoyed what you've seen here, please press that like button. If you haven't subscribed, please subscribe, and I hope to talk to you again very soon.